Hello again, everyone, and this is what I would call Rocket Science 2 or Rocket Science for Nerds, because after the previous video, Rocket Science for Dummies, I was requested to do some more research or to show things with this rocket simulator that I have, Simple Rockets 2. So I have here these rockets. I have the engine, I have the fuel tank, I have gyroscope, I have a nose cone, and I have a sensor that takes the reading and put it into an output file. I'm interested in the value of thrust, the craft mass, and the acceleration, because those are things that I talked about in the other video. So right here we have the acceleration is displayed here, and also you'll see it here. We have the velocity of the craft. I'll be launching vertical only, just to demonstrate some things here. Yeah, I think we're good to go. So now the acceleration is 5.5, and of course that's plus the 9.8 that's dragging you down, so the net acceleration is upward by 6.5 at the moment. And the amount of fuel, you can see it here, this one. And the thrusts, I want to show you the thrust, engine thrust here. And as you see, the thrusts 231 kilonewton, 32 kilonewton, 33, because this simulation is kind of very realistic, and it takes in account the reduction in atmospheric pressure. So here the air density here, I don't have a display for air atmospheric pressure. No, I don't, but I can put it. Yeah, it's in the game, but it's not in this one. So now the acceleration is 18, 19, and it's still increasing in 20. So keep it going until we run out of fuel. And now you see this, the speed is going like crazy because the acceleration is very high. Okay, we started with around 6 or 7, something like that. But look how much we have now. So I did the similar flight to this. I took the data and I put it in Excel sheet and showed some graphs that are amazing. That's it, out of fuel. And it's still rising up. And I want to show you something here. Look, the acceleration is 8.2. And the acceleration at this moment means that the speed is decreasing by this rate. Now let's go to the map and see what's happening. This rocket is going to go up and then reach the apogee and then falls again. The atmosphere in this hypothetical planet is at 58 kilometers only. So let's go do the graphs. So here's the graphs. There are 3 actually, and the first one is thrusts. And as you see here, this is the same 2 images from the previous video. Here, when we started the launch, the thrusts didn't just go to its maximum all of a sudden. No, it just took a couple of seconds until it reached the maximum. And then gradually, as time goes on and the rocket climbs to less atmospheric pressure, the thrust is increasing. And you see, this is from here to here. This is a very good percentage you gain when you go high. And the increase, the increasement stops, and it's now the same. This means we are in the vacuum of space. And in this simulator, the atmosphere disappears after 58 kilometers, not gradually as in reality. But yeah, according to the game physics, at this point there's no atmosphere, 0 atmospheric pressure, like absolute 0, and that's why we get this this flat line, no more increase in the thrust. And here, when I shut down the thrust, or the engine shut down, the amount of thrust is 0, and then I'll let it run for a few seconds after that. Now the next one is mass, and this is the mass, all of this here from 0 up to like 15,000 kilograms. And you can see by time, in 100 seconds, the rocket lost all of this mass. Where did this mass go? Went downward up towards the Earth in a crazy high speed. And here, when the engine shut down, there's no more consumption of the fuel, so the mass remain the same. Now, because the mass reduces that much, we expect the and the thrust increases a little bit, so we expect the acceleration to accelerate. So that's an increasing acceleration. At second 0, there was no acceleration. Then the acceleration started to increase. As the mass decreases, the acceleration started increasing. And can you see how much percentage that of increase? And here, this is like 8 Gs, more than 8 Gs, and that's enough to destroy any rocket, but not in this simulation. They're being kind with us. And when the engine was shut down, the acceleration was 9.8 meter per second. But there's a problem here with the game. It doesn't differentiate about the direction of the acceleration. Because when the engine is shut down, we should experience just the decelerating, not accelerating. Our speed should be dropping, not increasing. According to this part of the graph, this means that the rocket was gaining speed. So now let's put the three graphs all together. The thrust in green, the acceleration in blue, and the mass in red. You see the mass is decreasing, and the acceleration is increasing. And the thrust, of course, it doesn't care about anything except the atmospheric pressure, and so it kept increasing a little bit. Now I like to go back to acceleration. So this is acceleration. This is the actual acceleration that the rocket faced. Now I'll show you the calculated acceleration. Here it is. And in my calculation, I took care of this downward, or sorry, with the deceleration of the rocket, I made the deceleration to be negative. Now let's overlay both of them together. So the blue one is the acceleration, and the orange is the calculated acceleration. And you see that they are matching the same, almost. Yeah, almost the same, very much, until a certain point, maybe from here until here. Starts to be a difference. Where did that difference come from? Why the calculated acceleration is more than the actual acceleration? Because this calculated acceleration is just dividing the mass, dividing the thrust by the mass. It didn't take care of, or didn't mind the atmosphere or the drag. Now the higher speed we have, as you saw, the rocket was going so fast around this area. The faster you go, the drag would increase in exponential way, because it's a function of square of the speed. And as we leave the atmosphere, they are back together, almost the same. I think that's all. That's all for now. And I'm waiting for more questions. I'd like to explore more things. And thank you for Larry and Poppy.